Hi everyone, I welcome you all for the course of VLSI Design. It is a 3 credit course having 5 different course outcomes from CO1 to CO5. So we are going to start with the course outcome 5, that is named as Construct the VLSI System Components using Verilog HDL. This course outcome is also related with the laboratory courses that we are going to see under the subject named as VLSI Design Laboratory. We will start with course outcome 5 followed with the remaining course outcomes. To start with Unit 5 is the Introduction to HDL that has an outline of VLSI design flow followed with hardware description language and its associated parameters. So we are going to see all these topics under Introduction to Hardware Description Language. To start with is the VLSI design flow. This VLSI design flow comprises of these number of steps that are going to be involved. So in slide 4, you could see the various process that has been involved in this VLSI design. It starts with the specification that represents the design specification and proceeded with various steps, and it ends with the final chip that is fabricated, right? So we will see one by one step in detail. First step that is involved in VLSI design flow is design specification. What is this design specification is? This design specification represents the various parameters that are involved for constructing a particular IC. These specifications are designed based on the reviews that are given from the customers. So if I consider a customer, he would ask you to design a particular IC for a specification. So you need to design this specification concentrating on 3 different parameters. So the 3 parameters that will be involved is area, power, and performance. So when you are designing a product, the first and foremost is an area. If a customer requires the product to be a portable one, your area should be as minimum as possible. And while concentrating on area, the other parameters that are going to involve is power and performance. Performance represents how fast your device responds based on various clock frequency. And regarding power, it is going to demand long battery life in portable devices, and it shouldn't consume a larger amount of power dissipation. So these 3 parameters are the major parameters that needs to be concentrated while you are designing your specification based on the customer requirement. However, in VLSI, there will be a trade-off in these 3 parameters. If an area is minimum, you can't satisfy the power. If you want to satisfy the power, you have to avoid the performance. So anyway, there will be a trade-off between these 3 parameters. However, we can reduce these parameters as much as possible. We can reduce the power, we can reduce the area and improve the performance of a device. This is being achieved as much as possible. So concentrating on architectural design. So once you find what are the various design specification that is going to be involved in your product, the next step that is involved is the construction of the block diagram. So the step block diagram represents the architectural design. So in this architectural design, you could see a block diagram of a mobile phone, a smartphone device, where you are having a number of components that are being involved in this mobile phone. So while constructing the architectural design, the first step that needs to be involved is you need to start with the block diagram and you need to provide a rough sketch how these components needs to be interconnected, and the parameters that needs to be concentrated is area, power and cost of the design while constructing this block diagram. So the next step that is involved is RTL design. While finding out the design specification that is needed and after constructing the block diagram, you need to write a hardware description language. That hardware description language can be in two different styles. Either it can be of a Verilog or it can be a VHDL design. What does this RTL represents is, it represents register transfer level. What does it means? It means that you are going to write a hardware description language. Based on the coding style that you have written, it will be constructed into an architecture. That is what mentioned as register transfer level. You can write in any one of these coding styles that is available in this slide. In the right hand side, you could see that it is an RTL design of an half adder circuit, where this half adder circuit has been used in two different programming level, right? So the next step that is involved is verification of this RTL. What does this term verification represents is, we are going to verify whether that code has any fault in that code or not. How we are going to use it is by taking a test bench program. So we are going to apply test input vectors for the device under test that we have designed, and we are going to check the results and measure how much amount of fault is going to be created in our design. So to start with is creation of a test bench, and what we need to do is, suppose if I want writing a code for a test bench of a half adder, you need to do an instance. What is the meaning of instances? You need to call that program of half adder, and then only you are going to write a test bench for that half adder. That is what we created in the workflow of the second design. Instantaneate the design in the test bench, and then you are going to apply a test vector, compile the test bench, run the simulator, observe the output, and you are going to verify whether that logic of the design is as intended of your specification or not, whether it has done any violation in it. This is the initial step that is mentioned as RTL verification. The next step that is going to be followed is synthesis. So what do you mean by the term synthesis is, so far you have written a RTL code. Now what you are going to do is, you are going to convert this RTL code into a gate level netlist. While converting this RTL code into a gate level netlist, there are three stages of process that is involved. To start with is the translation, followed by optimization, and then a mapping procedure. So translation. What does translation represents is, you could see a image in a right hand diagram where the RTL code that is written either in Verilog or VHDL has been converted to a Boolean expression. That is what translation means. Translation is a process of converting a RTL code into a Boolean expression. Second step is optimization. What do you mean by the term optimization is, the Boolean expression is going to be optimized by using two different types of optimization methods. What are the optimization methods that is going to be employed is, one is sum of product and product of sum. So by using any one of the optimization method, you are going to optimize the Boolean expression. That is what optimization means. And the last one is mapping. Mapping is technology independent process where you are going to make the Boolean expression to a technology dependent process, right? So what we have done in translation, in the translation we have converted the RTL code into a Boolean expression. Next, what we are doing in optimization, by employing SOP or POS method, we are going to optimize the particular Boolean expression. And then what we need to do, we need to map. Map in the sense that optimized design needs to be mapped with the target technology. What does this target technology represents? The target technology can be any one of the foundry design. That is, it can be designed to 45 nanometer or 90 nanometer or 80 nanometer, whatever might be. So this optimization and mapping represents the conversion of a Boolean logic to a target technology that is available in your design. So this synthesis covers translation, optimization and mapping. And the next step that is involved is design for testability. In this case of design for testability, after doing the synthesis process, we are having a circuit under test, and what we are going to do under this circuit under test is we are going to add an extra logic into our design. So what does this extra logic means is, it is basically very similar to the DFT concept. That is, we are going to introduce a test logic into our design, and we are going to verify whether the obtained response matches with the expected response or not. For verification purpose, in this case, I have shown you with an example of automatic test equipment, where the circuit under test has been inserted with the test logic, and we are applying a test pattern to the circuit under test. And when we are observing the actual response, this actual response should be matched with the expected response, and we are comparing whether it is pass or fail. If it is pass, the design logic is okay, or else if it is fail, there is a fault in our design. We need to identify where the fault is, and we need to rectify that fault. We need to do a backtracking process. That is what carried out in design for testability. Next one is the floor planning. So after doing this design for testability, you will be in a position to identify what are the various components that are involved in the design. Now what we need to do is, we need to draw, or we need to place the components in that particular area. So how we can place the components is, the initial step that is involved is, we need to create a rough sketch. Rough sketch in the sense, where to place the components. If I place a component like this, whether my area will be reduced or not. Or if I place the component like this, whether my power consumption will be reduced to a greater extent or not. So these needs to be done through a rough sketch, and it is named as floor planning. So in the case of floor planning, the main objectives that are involved are to minimize the area, timing, wire length. When we reduce the wire length, the routing becomes easier. And finally, we need to reduce the voltage drop, that is represented as IR drop. So these are the main objectives that needs to be considered when you are drawing a rough sketch of where to place the components. This step can also be compared with the construction of a floor plan. That what you use to construct a building, when we are constructing a building, we used to prepare a floor plan, right? We simply draw a sketch for a particular land area, and we will be deciding how much amount of space can be allocated in a room. Similarly, here what we are going to do, we are going to draw a rough sketch how to place the components close together in such a way that area, timing, wire length are getting minimized. That is what carried out in floor planning. Next step represents the placement of block, where you can do the placement of block in two different manner. Either you can go for a standard cell placement or a building block placement. Standard cell placement in the sense, in the left hand side you could refer an image where you are having two different types of cells. In this, the power supply are being kept at the top, ground are placed at the bottom, and clock are placed at the midway between VDD and ground. So what does this represent is, in the case of a standard cell placement, you can't alter the position of the power supplies and the clock signals that is involved. That is what a standard cell placement is. So when you are going for standard cell placement, VDD needs to be placed at top, ground needs to be placed at bottom. Whereas if I am moving on to building block placement, I can place my power supplies according to my convenient of my design. Even I can place my power supply at the bottom, and I can take an adapter and connect it at the bottom of the design. This is what done in building block placement. So while you are placing a block, either standard designs can be followed, or you can place the block on your own. That is what placement represents. After placing the blocks, before making the interconnections, the major step that is involved is clock tree synthesis. What is this clock tree synthesis is? In this clock tree synthesis, before going to definition, let me explain the cases that is available in the figure. When you see or look into the figure 1, this figure 1 comprises of number of flip-flops that are being going to be controlled with the help of a single clock, which means it is an example of a synchronous network. So when you are using a common clock for all the flip-flop, we can't ensure that all the flip-flop will be made on simultaneously. Each and every flip-flop will be experiencing a variation in time. The flip-flop that are placed nearer to the clock will be switched on at one particular interval, whereas the flip-flop that are being placed away from the clock signal will be experiencing a further delay, right? So in the process of clock tree synthesis, what we are going to do is, when you refer to the figure 2, you could see that there are number of buffer and inverters are being placed in the design. The main purpose why we are going to design or we are going to insert these kind of buffers or inverter is to balance the clock delay. That is the main purpose that we are going to do in this clock tree synthesis. So in this clock tree synthesis, after placing the components, before providing the interconnections, we need to balance the clock delay to all clock inputs. So balance the skew and minimize the delay, we are preferring clock tree synthesis. Now I mentioned the word as skew. What does this clock skew represent is, you consider two different types of flip-flop. When you apply a common clock for both the flip-flop won't be on at the same time. First flip-flop will be made on immediately, second flip-flop after a time. The difference between the time interval represents the clock skew, and you need to design the circuit in such a way that this clock skew is minimized as much as possible. That is the main objective of the clock tree synthesis. And after you are balancing that particular portion, then you can make the routing connections. Routing connection in the sense, we have placed the components, now we are going to interconnect the components. While doing this kind of interconnection, routing offers two different classification. One is, either it can be a global routing or it can be a detailed routing. What is the basic difference that lies between these two different types of routing is, when you look into the figure A, you could see that the components are being connected in a random manner. The length of the wires are being ignored. You can also take a longer wire, connect between two different components. What happens in this case? We are going to increase the delay, right? But how the objective should be? While connecting the component, we need to reduce the wire length as much as possible. This will be attained only when you are moving to detailed routing. So what is the meaning of detailed routing is, it ensures each net satisfies the required timing budget at a low rate. That is what the detailed routing ensures. So when you are designing or when you are making an interconnection, you need to prefer detailed routing rather than a global routing. If you are taking a global routing, the limitation that is going to be caused is delay. You need to sacrifice or you need to ignore the delay while you are going for this kind of global routing. The next step that is involved is sign off. What you mean by sign off is after making all the interconnections, before going to fabrication, you need to do some basic verification process. That verification process will be carried out in three different levels. Either it can be a logical check or a physical check or a power check. What does this means is logical check. Apply some input vectors, observe the response. That is logical. Physical, you are going to verify whether there is any short circuit connections or whether there is any open circuit connections in your design. That is physical. Power check is you are going to verify whether it satisfies the operated voltage or not. Whether the product that you have manufactured meet out the electrical characteristics or not. So these three parameters will be analyzed in the case of power check. In the next case, we need to go for fabrication. So after doing sign off, what we are going to do is our design will be converted to an encrypted format. That encrypted format will be a graphical data stream format that is represented as GDS2. So in this case only, the total design is being converted to a chip that is being done by the manufacturing process. Now, while doing this fabrication, before going to mass productions, we need to verify whether the product that we have manufactured has met out all the electrical characteristics or not. So we need to go one more step of verification, or else if I go without or if I go ignoring this verification to a mass production, and if there is a fault in any one of the portion, the entire ICs under mass production are going to be wasted. So what I need to do is, after fabricating using the manufacturing process, using various manufacturing process, before converting into a mass production, I need to do packaging and testing. Where packaging and testings are carried out in 5 different levels, right from assembly out, DC test and burn in, monitoring burn in, post burn, and final test. To start with is an assembly out that deals with the number of input and output pins that is involved, quantity, and also process design. DC test and burn-in indicates the various DC test, reliability test, high stress test. Monitoring burn-in means that you are going to monitor the IC under various operating conditions where shorter test times can be involved and several tests needs to be carried out frequently. Then we need to verify the electrical characteristics under room temperature and under cold temperature, and this is accomplished in post burn-in test. Finally, an IC test is being carried out under high temperature, and then only your IC will be ready for mass production. So these will be the various steps that are going to be involved in VLSI design flow, right? So nearly 10 to 15 steps are being involved. To consolidate, what we can do is, it starts with system specification, followed by architectural design, functional logic, functional and logic design, circuit design, physical verification, where placement, routing, clock tree are being involved, then verification and sign off, then post-processing, fabrication, packaging and testings are being involved in VLSI design flow. So this is the various steps that are involved in various design flow. Using this concept, we will move on to the next topic of this particular CO, that is An introduction to hardware description language. So what does this hardware description language represents is we are going to describe the hardware at various levels of abstraction. It can be of two description. One is either it can be a structural description or a behavioral or functional description. We are going to use two different set of logic levels. We are going to use two different programming styles. Either we can go for Verilog or we can use a VHDL. And simulation semantics are going to be done using various tools like Model Sim, or you can use an active SGL, or we can go with Xilinx platform, or we can also use Quartus PrimeLite software. So any one of the simulation platform can be used in this. To start with the basics of Verilog is the first we need to concentrate on modeling structure. So while writing any styles of Verilog, the keyword begins with module and terminates with end module. And what you have to remember in Verilog is all are case sensitive. You need to write all the keywords only in lower cases. Upper cases are not allowed at all. You can use white spaces just for your readability. While declaring any statements, you need to terminate any statements with a semicolon. If needed, you can use comment line. A single line comment will be denoted using two backslashes. Multi-line comment will be denoted using backslash, two stars followed by a backslash. If required, you can use timing specification for your simulation. This is how a modeling structure of Verilog will be. We will start our basics of Verilog initially with the number representation by using the various components of Verilog. So this slide indicates the entire blocks that are being carried out by Verilog under various different levels. So the module declaration has port declaration, data type declaration, circuit functionality, and subprograms that are going to be involved. So when we complete this block diagram, the entire chapter will be completed. We will move step by step. To start with this, a logic values of Verilog. So there are four different logic levels: logic 0, logic 1, high impedance, and an unknown state. When you are representing a logic 0, it can be also used for denoting a low value or for a false value. Similarly, for representing a logic high, it can be used for one or true expression. High impedance status are described using the notation Z, and an unknown condition will be represented using X. So these are the four logic values of Verilog. And regarding the number representation, the numbers are represented using the following syntax. When you refer the second point, it is mentioned as size, followed by a backtick, signed, radix, and its corresponding value. What does the size represents? You know that when we are trying to represent a value using digital numbers, we used to denote it using bit. So it can be a 2-bit number, it can be a single bit number, or a 4-bit, or a 8-bit, or a 16-bit, or a 32-bit. We can use any one of the size for representing our Verilog expression. And this is followed by a backtick, and you need to indicate the signed value and a radix of a number. Radix of the number in the sense, it has four different cases. It can be a binary number, it can be an octal, or a decimal number, or a hexadecimal number. So using any one of the base, you are going to represent the representation in a Verilog. I will also show an example for this, for number representation using some model sim software, right? And we will be discussing while we are doing the laboratory sessions, right? For example, let me give you one example. My representation is 4 tick B 1000. What does it means? The size of the bit is 4 bits. We are going to use a binary representation having a values of 1000. This is how you need to do a number representation in Verilog. We will discuss this in the upcoming classes, right? So in today's class, what we have seen is, we have seen a VLSI design flow followed by an introduction to hardware description language and what are the various logic levels in a Verilog and number representation in Verilog. In the next upcoming topics, we are going to discuss what are the various operators in Verilog, the data types, scalars and vectors, event control, assignment operations, blocking and non-blocking statement, different coding styles like gate level modeling, data flow modeling, behavior level modeling, switch level modeling, structural level modelings of Verilog in the preceding classes. So this is for today's class. Thank you all.